Okay, in this video, we're going to continue the work we started in part 1, where we are looking at scalar surface integrals. So in part 1, we worked out the first example, where we're finding the surface area of a paraboloid. We're going to go on to example 2, where we are finding the total mass of this surface z equal x cubed plus y over a domain in the first octant. Y is ranging between 1 and 4, x is ranging between 1 and 2. The density of this surface, we are told, is given by x cubed y. Okay, so here we go. So that means in this case the phi in our formulation for this integral is going to be the position for phi is going to be taken by the density. So let's just start with a little sketch, perhaps, before we continue. So if x and y are a bit like this, so that is x, that is y. So the way this surface is going to be shaped like is something like this. It actually goes to 0 as x and y go to 0, so it's going to be something like this. Then we are interested in the region where x is between 1 and 2, y is between 1 and 4. So if you go to the xy plane and trace a region something like this, and then if we project these upwards, so we might have a point there, a point there, a point there, and this one another point there. So you might have something like this. So that could be the region of interest. Okay, so the mass of this is going to be given by the double integral of x cubed y. Then we are going to use the formula number 2. This is fy, and then dx dy. Now in this case, our f is equal to x cubed plus y. So fx is 3x squared, fy is 1. So the mass is going to be given by double integral of x cubed y. Then here we're going to have 1 plus 1 plus, it's actually going to be 9x to the power 4, because it's the square of that, dx dy. And then x is ranging between 1 and 2, 1 between 1 and 4. So let's simplify this and see what it looks like. So what we're going to have is x cubed y into the square root of 2 plus 9x to the power 4 dx dy. Again, we can separate variables here, so we can simply write this as I'm just going to write the y integral here, 1 to 4, and then the x integral here, x cubed square root 2 plus 9x to the power of 4 dx. This is because these functions are just products of x and y, and the limits here are constants. So whenever that condition is met, we can separate the terms. The x integral here, we can use substitution. So if we let u, simply because derivative of x to the power 4 is a multiple of x to the power 3. So if this is u, then du is going to be 36x cubed dx, which means 1 over 36 du going to be x cubed dx. Then when x is 1, u is going to be 11. When x is 2, u is going to be 146. So that means, going back to our integral, the mass is going to be the integral for y squared over 2, 1 to 4. Then we're going to have 1 over 36 into the integral of it's just going to be square root u, really, from 11 to 146. So the y integral is going to give us 16 minus 1, so it's going to be 15 over 2, 1 over 36 here. If we integrate this one, we're going to get 2/3 u to the power 3/2 between 11 and 146. Then plugging in the limits, so this thing is going to simplify 2. So these 2 cancels out, this goes here 5 times. So we're going to have 5 on 36 into 146 to the power 3/2 minus 11 to the power 3/2. So that's going to be the mass of the surface in the domain described. Okay, so there's one more example, number 3. Okay, so at this point we're going to recommend that you have a go at number 3. You can pause the video, work through it, then when you continue the video you can compare with our answer. Okay, we are now going to scroll down to our solution of this example number 3. By the way, if you've got any questions on any of the material we're doing, please feel free to post them in the comment section. If these are useful, of course would like to hear your feedback about them. Do post your comments in the comment section, and do not forget to subscribe and like the video and share accordingly. Alright, so in number 3 we've got a paraboloid of revolution. Its shape is going to look something like this. So basically we just start with a parabola that is upside down, and then if you rotate it about the z-axis, then you get this paraboloid of revolution. We are interested in the surface area of this shape above the xy plane, so that means above z equals to 0. If you plug in z equals to 0 here, then you get x squared, let me write it here, x squared plus y squared equals to 4. So that means this lower boundary here is the circle, x squared plus y squared equal to 4. So that's going to help us when it comes to the limits. Now this function is in the form z equals 2, so we can use this formula here. in which case our f is this function here. So derivative of f with respect to x is minus 2x, with respect to y is minus 2y. Then if so here we're just finding the area, so this function here is going to be equal to 1. So this is just going to be the term in the integrand. So if we plug in here, this is what we have. Now seeing that we've got this group of terms here, and our region in terms of xy is a circle. Once we have that, then the natural thing to do is to transform to polar. We transform this to polar. The this term is going to be the square root of 1 plus 4r squared. Then dx dy is going to transform to r dr d theta, where this term here is the Jacobian of the transformation. Then the integral in r we can evaluate using u substitution. Let u be 1 plus 4r squared. Then r dr, which is what we have there, is going to be 1 on 8 du. The limits will change from 0 to 2 to 0 to 1 to 17. The theta integral we can evaluate straight away. That's going to be the u integral. So this thing works out to pi on 6 times 17 to the power 3/2. If we express the function in the form something equal to 0, so which something is going to be our g, to use the other form of the formula, then our g is going to be z plus x squared plus y squared minus 4. We just take everything here to the one side. Then the gradient of g going to be 2x to 1y. It's just derivative of x. G with respect to x, g with respect to y, g with respect to z. Take the magnitude of that, we get this term here. So it's not mass, the area. So the area is simply going to be this integral here. Now we notice here, once we get to this point, that this is exactly the same as what we have there. So the rest goes exactly the same way. And then for this example, just for instructional purposes, we're also going to demonstrate the parametric formulation. So the parametric formulation is just going to make use of the polar transformations here. So make x equal to r theta, y equal to r sine theta. Then z is going to be 4 minus r squared. Then the position vector x, y, z is going to be r cosine theta, r sine theta, 4 minus r squared for z. Then here you notice that our two parameters or our two variables are r and theta. So differentiate this with respect to r, that's what we're going to get. Differentiate this with respect to theta, that's what we're going to get. Then if we do the cross product of that, we'll take this and slot it in here, this one. There, the x component is going to be 0 plus 2r squared cos theta. The y component is going to be 2r squared sine theta minus 0. And then the z component is going to be r cosine squared plus r sine squared. So it's just going to be r. Then we take the magnitude of this. This is going to be 4r to the power 4th cosine squared plus 4r to the power 4 sine squared. This is going to be r squared. So this is 4r to the power 4 plus r squared. We factor out r squared and we get this. And then when we plug it now into our formula, so that's going to be the integrand. The differentials will be in terms of our parameters, so dr d theta. because r varies from 0 to 2 and theta from 0 to 2 pi. But then once we get to this point, we notice that this is identical to the integral here. So the rest continues exactly the same way. All right, thank you.